I already know I'm gonna struggle with writing big enough, so if it gets shrunk, just let me know. Also, I didn't quite know how to gauge the seminar, so it might be even less than 1 hour, because this is supposed to be a complement of the seminar that Mario Carliner gave like a month ago or something. So I don't want to repeat too many things. I think I want to give the other side of the story. And let me start by acknowledging the fact that like the stuff that I'll be telling you, I've learned it, understood it or whatever from collaboration, interactions or arguments with these people here mostly. And so this is my outline. The thing that I'd like to tell you is first a somewhat broad introduction towards the problem with heavy exotic mesons, somewhat historically also. And then I'll describe to you the two possible solutions to these problems, or possible linear combinations of the two, which is tetraquarks versus hadron molecules. And then I'll try to give you these 3 points, which in my opinion are 3 possible set of observables that are, if you want, universal enough, that are able to discriminate between the two possibilities, but at the same time are universal enough that don't rely on the particular realization of the system that you have in mind. Okay. The first one is the study of low energy scattering using non-realistic effective theories. The second one is the study of prompt production of these objects. I'll tell you what everything is when it comes to time. And then this is not yet well established, but it's a pretty tantalizing observation in the strange sector. So to start from basics, we know that in principle, there is nowhere written in QCD that hadrons should be only mesons or baryons. Okay, the rules of the game are gauge invariance and confinement. So we only see color singlet objects. Okay, and so far we have been used to the standard mesons, QQ bar, the 3 times 3 bar, which is, you know, it contains a singlet, and baryons, which is 3 times 3 times 3, which also contains a singlet. However, following these rules, in principle, no one forbids other more exotic structures, which are the topic of this seminar, as, for example, tetraquarks, or let's say states with 4 quarks. But also, for example, stuff like glue balls. Glue balls are, if you want, hadrons made of many gluons with no quarks, because every time that I take a tensor product of an imaginary representation of SU3, any number of imaginary representations, there's always a singlet. And again, nowhere it's written that we only must have these 2 guys. Okay? In principle, we could have all these possibilities. And this is a long-standing question in QCD. People have looked for this stuff for a very long time without success. And the reason, at least in my opinion, is because these objects here, glue balls also received a lot of attention, were mostly looked for in the light sector, meaning in the set of hadrons that contain light quarks, in which case, first of all, in my opinion, it's not even clear what it means to have these versus, for example, just 2 mesons, because there is no separation of scales. And second of all, there is a very practical experimental problem that is, for example, an object like a glue ball would decay into a bunch of stuff like pions or light mesons, just like other mesons could. So to experimentally tell, oh, we are seeing a glue ball versus we are seeing a mildly heavier meson is a tough business. And good. The situation changed in 2003, where the first one of, well, what we now know is one of these objects was discovered. And this guy is called the X3872, which will come about in the seminar very often, because that's essentially, it's the most studied of this object, and is by far the most peculiar one, and I'll tell you why. And this guy was discovered in the decay of the B meson into a kaon and, well, itself, okay? And you see, the fact that it was discovered in the decay of the B mesons, it means that there are heavy quarks involved, okay? And in fact, since then, a bunch of these states, since 2003, started popping out pretty much everywhere. But the peculiarity is that all of them were discovered in the setting of heavy quarks, okay? And so for now, we know that there exist states that are of this kind, CC bar, and then 2 high quarks. We have also observed states that contain the bottom quarks. Okay. And recently, and this is what Marek Karliner was telling you about, we also discovered states with 2 charms rather than a charm and an anti-charm. But also, and this is very nice, we have observed a state that only has heavy quarks, as well as pentaquarks, stuff with stuff like this. Okay. And as of today, I think we have roughly something like 20 to 30 states of this kind, which I mean states that if you look at your favorite table of, for example, Quarkonia predictions, they are like completely off that table. Okay. So their quantum numbers are not what you would expect. Their masses are not what you would expect. And some of them are clearly manifestly 4 states. I'll tell you in a second, okay? So this is just to say that I think as of today, this is a compelling problem of QCD, to the extent that we have a very nice theory like QCD, and we still don't really understand its spectrum, okay? Good. So what are the peculiarities of these states? I've reported some of them there, but let me list what makes them exotic, okay? And some of these properties that are listed are shared by all of these states. Some other belong to only some of them. So it's a bit of a complicated system, but the idea is that all of them have masses and quantum numbers, which I mean typically I mean spin, parity, and charge conjugation, which are unexpected for Sharmonia, or at least the combination of the two are unexpected from Sharmonia. Okay. They're pretty much all of them are anomalously narrow. And by anomalously narrow, I mean that all of them, were they Sharmonia, could decay into mesons with a large phase space, which would imply that they should be broad, okay, they should have a very short lifetime, but that doesn't happen, okay. As you see, for example, these states here, they're very narrow. Like the first one, the X3872, it could decay into DD, for example, with a phase space that is hundreds of megaelectron volts, but nonetheless it doesn't, and its width is between 200 keV to 1 MeV. So this object is a delta function, essentially, which is it's very weird to explain if you assume there is a Sharmonian, for example. Okay. Then the other thing, and this is only true for the X3872 so far, they are hadrons and they decay strongly, but their strong decays violate isospin. And by that, I mean that, again, the same X3872 that you saw before, okay? It has been observed decaying into J psi rho and J psi omega with essentially the same width. And for those who don't know, J psi is a charmonium with a charm and an anti-charm quark, while the rho and the omega are light mesons. They have only up and down, okay? But this guy here is an isospin triplet, meaning that it comes in a neutral and charged state. While this guy here is an isospin singlet, we only have the neutral component, okay? And where isospin exactly conserved, you would either decay in one or the other. dx decays in both and equally likely. Okay.
So this is a weak decay?
This is very well.
These are weak decays you're talking about?
Yeah.
So you expect isospin violation, don't you?
No, so weak decays. No, they're strong decays. They're strong. Yeah, the time scale over that happens is the time scale of strong decays. So no, if you were it to be a charmonium, you would not expect isospin violation there. It would decay, for example, in J psi, in omega. If it's an excited charmonium, it decays into a J psi omega. That's okay. Good. And then, okay, well, one thing is more obvious. Some of them are charged. Okay. Some of them are charged. And the fact that they are charged tells you that they must have 4 quarks. Because let me bring you, for example, if you look at the Z sub C there, that object is discovered in this channel here. Z sub C that decays into J psi and pi plus. Now the J psi contains 2 heavy quarks. So there is no way that you can produce them from vacuum fluctuation with a decent rate, which means that the 2 heavy quarks must have been in here in the first place. And then the final pion is charged, it doesn't have the quantum numbers of vacuum, which means that also these guys must have been here in the first place. So for this object and many others, the Z's there, for example, they are manifestly 4 quark states, like CC bar, QQ bar. Good. And then there are, I'm running out of space already. And this is another crucial property. They are very close to threshold. And by very close to threshold, I mean that their mass is extremely close to the mass of a pair of mesons. Depending on what state you're looking at, you have to consider different pairs, but they're very close. It's what I call epsilon there is the mass of the state minus the mass of the closest pair of mesons that have the same quantum numbers as this state. And as you can see, some of them, all of them are like very, very close, like tens of MeV. Keep in mind that the typical scale of QCD, it's hundreds of MeV. Okay. So 10 MeV is very small, and dx is particularly anomalous. It's like less than 100 keV away from the threshold, the D0, D star 0 star, D star 0 threshold. Okay. And finally, the last peculiar property is that if you look at the decay width of these objects in the threshold itself, meaning the decay width in those mesons that are very close to the state, this is anomalously large. This is the second column, third column, and you see they're like 40% for dx, almost 90% for the Z sub B's, 70 for T's. And this is again something you would not expect because they are so close to threshold that the available phase space is extremely small, which in turn means that they are very strongly coupled to the threshold itself. Okay. Is this clear, more or less, what the picture is? All right, so let me try to tell you now, this is the historical picture, if you want, why these things are puzzling. And now let me try to tell you what are the 2 main interpretations of these objects. Because if you want, the question that we would like to ask is, do these exotic objects like those, of course, to some extent, it's a triviality. You know, I mean, if I look at deuteron or whatever nucleus, there is a many quark object, of course. I'm making color singlets out of already color singlet objects. So we are somewhat part of that object, right? So the question is QCD alone able to generate objects like that at scales comparable to the hadronization scale? So 1 Fermi or less than that, for example. Good. And the two main possibilities to explain what these states are, or again, it could be a linear combination of the two, we don't know, are the Tetraquark model and meson molecule. Okay. So in this interpretation here, we think of these states exactly as very close relatives of standard mesons and baryons. Okay. So it's some stuff that is produced by QCD, short distance, no perturbative QCD, okay, whose, if you want, whose typical size is of the order of the Fermi. Okay. So if you want to picture it, it's something that looks like this. Heavy quark, anti-heavy quark, and then light quark, light anti-quark in an object that is roughly 1 Fermi, and they interact with each other through honest to God gluon exchange. Okay, so short distance you see. Okay. A meson molecule instead, it's precisely the analog of what happens, for example, for the deuteron. So much so that this guy, the X, for a very long time, it was called the deuteron or whatever for a long time, because it was thought to be like the meson analog of the deuteron, where you have two separately colored singlet objects that themselves are separately generated by short distance QCD, whose binding is due to long distance effects. Okay. Again, if you want a picture, it's something like this. Quark, an anti-quark, which form one meson, and then on the other side you have a quark and an heavy anti-quark form another mesons, and this guy talk through light meson exchange, pions or rhos and stuff like that, and that causes their binding into a molecule. For example, for the deuteron, this happens through the exchange of pions. Okay, you have proton and neutron, they exchange pions with each other, and that creates a bound state. Okay. Good. So now let me try to compare the two ideas. And maybe I should, yeah, for the sake of intellectual honesty, I should say that I'm going to try to be as unbiased as possible. But I work on these, so some bias will emerge for sure. Okay, so I'd rather tell you in advance. Okay, all right. So I said this is we mentioned it as generated by short distance QCD, like mesons and baryons. In this model here, the closeness to threshold. Well, maybe I don't have to write everything. But the fact that these objects are close to threshold, as I'll explain later when I show you the non-relativistic effective field theory, is essentially due to two instances, okay? The mass, the bare mass of these states is generated by your short distance interactions, okay? So that's something you have almost no control over, okay? And that can happen in, it's a somewhat like, you know, you have many of these states, and in general, you expect the bare mass of these states to be of order lambda QCD away from threshold, okay? However, as I'll show you, this is what happens in most of the time. We think that's what happens most of the time. But the fact that these states do interact with their own threshold will push the renormalized mass, meaning the physical mass, much closer to the threshold as you would expect. Okay. The nice feature, but at the same time somewhat unfortunate feature of this model is that it's very rigid, because these things at these states, just like mesons and baryons, in which case we know that, for example, the spectrum of mesons and baryons, it cannot be anything. It's forced by symmetry. You have, you know, flavor symmetry and spin symmetry and stuff like that. And you know, the eightfold way is the eightfold way. Mesons have to be on the multiplets. Okay? Same thing happens here. And in particular, in the most common realization of this model, one thinks at this state as what's called the diquarkonium. A diquarkonium is something of this sort, where you think about the tetraquarks in terms as ijk, so qj, qk. This is what is called a diquark. So you see, it's two quarks, but put together in a colored configuration. This is an anti-triplet, okay? Which, however, when you put it together with an anti-diquark, it can form a color singlet. Okay? And if you buy this picture, then you can compute the spectrum. And in particular, there is this purely phenomenological. I don't think there is any QFT derivation of these. But it turns out that, for example, for mesons and baryons, it works very well. You have a phenomenological Hamiltonian where the mass of your state is given by the sum of the masses of the constituents plus some spin interactions. Okay. And wow, I'm running out of space already. And you see, the peculiarity of this thing is that to make it work, meaning to be able to reproduce the observed spectrum with this Hamiltonian, you have to assume that the spin-spin interaction only happens within the diquarks, meaning that quarks interact with each other, antiquarks interact with each other, but there is no cross interactions between quarks and antiquarks. Okay. For now, let me just assume it as an empirical fact. Okay. If you do that, you use this Hamiltonian, you can borrow these couplings from experiment, and you can predict the spectrum of these guys. And this is very successful at reproducing the X3872.
Angelo, are you using constituent quarks here?
Sorry, what?
Is this out of the non-relativistic quark model? What are the masses of the light quarks that you're putting in here?
Oh, good. No, the mass of the light quarks here don't really enter. I'm thinking in terms of constituent quarks. Actually, not even that. I'm thinking in terms of constituent diquarks.
Got it.
Okay. It's a bit of a mixed picture where the for the spin-spin interaction, you remember that you have actual quarks inside the diquarks. But then when you consider the masses in here,
The masses of the diquarks.
yeah, some dressed object, okay, whose mass there is no way that you can predict. I mean, you take it from experiments, okay. For example, these diquarks are the same objects that one uses to build baryons. So you can borrow some of their masses from heavy baryons, for example. Okay. You use the same thing. And you can show that there is the X3872, there is this Z sub C there, which has a mass of almost 4 GeV, and there is the Z sub C prime with a mass of 20 MeV. However, and this is the biggest problem of this idea, is that precisely because this is rigid, there are other states that are predicted by this model. Okay? And in particular, you expect, first of all, so these objects, the Z's, are observed both neutral and charged. The X is observed only neutral. So you would expect the charged partners of the X. Okay. On top of that, if you do, the usual Fermi statistics, spin parity, flavor, and sort of stuff, you expect 2 scalar states and a tensor state in the same thread. Sorry, I should probably mention this is the CC bar QQ bar. Okay.
What's the difference between an X and an C?
Is the charge conjugation. The X has plus charge conjugation, the Z's have minus. But they are expected to be degenerate. And in fact, this is, I should also say that all these kinds of constituent quark models, they have natural theoretical uncertainties that is some 30 MeV usually. Okay. So if you see something being off by 30 MeV, that's actually okay. We don't have, this is not an EFT, so we don't have control over what are the next reading order corrections. Okay. And so the main problem of this model is that these guys are nowhere to be found. Even though I'm not sure if it's my own ignorance or whatever, but I never managed to get a clear answer for someone that said, yes, we have looked for them, we haven't found them, and for some reason decided not to publish the analysis, or we just have never looked in the right places. So this is unclear to me. Okay. But let me say that this is the main complaint that people have. You see a bunch of states and you don't. And then the other big problem is that it's not clear how you can explain the branching ratio into states that are such close to them in phase space being so large. Okay, so it somewhat necessitates some more. I mean, we have ideas. For example, there was an old idea by Wilczek who thought that maybe once you study the potential between diquarks, this potential have a repulsive barrier at short distances, because if you take two diquarks, you bring them together, at a certain point you would like to form mesons out of them, but to form the meson you have to break the diquark first. The diquark has some internal binding energy, which would cause maybe a potential barrier. And if that was the case, it could explain why you prefer to decay in open mesons, because it would correspond to the tunneling of a heavy quark versus tunneling of a light quark. I think it's honest to say that we have conjectures, but we never managed to make it quantitative to say, oh yeah, we have this model that can explain those standards.
The diquark made out of light quarks is supposed to be pretty large inside.
It is, yes.
So maybe it just can't be viewed as an elementary object.
No, it's true, but all these diquarks are heavy light. It's like CQ and C bar Q bar. So there is a separation of scales that you can say, okay, well, I have a somewhat point like diquark. That is
But for some of the mesons, there was a picture where you make a diquark from two heavy ones.
Yeah, but I think it's only for these guys. For the one with two charm quarks, which are
for this GCC, the one that
precisely, I did this guy here. For the others, it's always either heavy light or very heavy, even for this guy.
If we did have two heavy quarks, there definitely is a diquark bound state, right? There's a 3 bar that the 3 bar channel is attractive.
Yes.
So you really would have them, and so such things would exist for like
Yes.
heavy guys.
In fact, for example, I should say that, and I never understood to what extent these calculations are reliable, but I think they are. There are evidences on the lattice of the existence of diquarks. If you put 2 quarks and 2 antiquarks on the lattice, you can show that they tend to arrange themselves in quark-quark, antiquark. Okay, I think it's fair to say that there isn't really a separation of scale that you can say, oh, this is definitely like this, but it's one side does look substantially larger than the other, let's put it this way. Okay, good. So this is for the tetraquark. For the molecule instead, instead of being the analog of mesons and baryons, it would rather be the analog of deuteron or other like nuclei, where you have separate or singlet objects which are bound by some mechanism. And again, just in contrast to this, and luckily for this, it's a less universal model, meaning that depending on what state you're looking at, you could have different components of this molecule, and depending on what components you have, the binding mechanism changes. Okay? Which means that it's less constraining. It's more acceptable to have some states and not other states, because, for example, for the other states, you might just not have any binding mechanism. Okay. And of course, it's in this model here, and I should stress that these are loosely bound. If they are not loosely bound, then again, there is no separation of scale that allows you to tell, well, this is a molecule versus this is a tetraquark, okay? And in the loosely bound molecule picture, of course, the fact that they are close to threshold is not a feature, is the reason for the very existence of the state. If we were not close to threshold, it would not be a loosely bound molecule. So it's sort of tautology to say, oh, it's a loosely bound molecule close to threshold. Again, it's in this picture is instead very natural to explain why the decay rate in its constituent is dominant. But at the same time, the other viewpoint is that it's not clear why you do have decays in other stuff. Because let me stress that, yes.
large n point of view, meson interactions are weak, right? So yes, maybe it makes sense that things are very near.
Yeah, no, precisely, exactly. Well, it depends though, because for example, if you want, loosely bound states can also be created by point-like interactions with a strong coupling, actually. If you have like a delta function potential with a large constant in front, that does create a loosely bound state. So it's, I don't think it's necessarily true that you must have weakly coupled mesons to create a loosely bound state. But you see, let me stress that since these states are terribly close to threshold, the X3872, for example, is so close to threshold that its radius, if you were to be a molecule, it would be 30 Fermi. 30 Fermi, I don't know, it clogs your sink. And you see, so now it's hard to understand if I have a molecule like this, where in the case of the X, you have a charm quark here and an anti-charm quark here. How can it decay, for example, 10% of the time into J psi, where now you have a charm quark that has to travel 33 Fermi on the other side to annihilate. Okay. So it's, you know.
This picture that these are two spin one guys or something, and there's some attractive pion exchange.
Yeah, no, that's precisely it. Yes, exactly.
They're really far apart from each other, so they're not gonna. There's no way they're gonna have.
And in fact, that's typically the complaint that we have. Like, okay, yes, it's very natural to say I'm mostly decaying into D star because it's just a fall apart of the molecule. By the way, I should say that if you study the width into D star, it's almost the same as the width of the D star itself, which makes sense. It's like, oh, this is somewhat stable molecule, and then it decays because one of the two components is dying. Okay. But the width of the state itself is much larger than that. So, or if you want, and this is maybe, yeah, it's the semi-classical picture that Ratazzi was talking about. If this were to be a molecule, we know that the time it takes for the molecules constituent to go around each other is 1 over the binding energy. Sorry, 1 over the width. So this state would be a molecule who doesn't have the time to go around each other once before dying. Okay. Yeah.
That just seems to kill this picture completely.
Sociology is. No, but it's true. I have to be honest, it's also true that the Tetraquark model, as much as I think is the solution to this problem, has these open issues that no one was able to address yet. And
Can you say again what the main problem was? That you don't see the other states? Is that the main problem?
Yes. Okay, and then there are 2 other things. So this is an accepted problem of this model, just like the missing states is an accepted problem of the model. And another accepted problem of the meson molecule is the prompt production, which I'll tell you in a bit. But to give you a sneak peek, is the fact that we do observe this X3872 produced at the vertex of the proton-proton interaction from D mesons who are recoiling from each other with relative momenta that are order 10 G. How do I bind? Okay, so okay, and then, but this is very recent. It seems to me that this model here does not fit the low energy data, which I'll explain in a second. Quenching. Okay. Is this clear more or less? Am I making a terrible mess now? The picture is clear. Okay. Oh my God, I'm not that tall. So let me describe what is so far my favorite description of what the problem is, which is in terms of effective field theories. I'll do it with a toy model because I don't want to waste time thinking about the spin of these particles and similar stuff, but the toy model captures all the features that we're interested in. So. All right. So the idea is that we want to describe a system like this, where most of these states are very close to threshold, okay, which means that the momenta involved are much smaller than the typical energy scale of QCD, which, for example, in this instance is the Pion mass, okay, which is, it's the ideal setup where you have separation of scales and you can build an effective field theory, okay. So we will describe a toy model for this, where it's a non-relativistic effective field theory for 3 fields, okay. 2 of these fields, psi1 and psi2, will describe the threshold mesons, okay. And there will be non-relativistic fields, so I'll have a psi1 dagger, I d0, actually plus psi1. Same thing for 2, okay. And then the third state, which is supposed to describe the exotic meson, will also be non-relativistic. Let me call it psi3, but I'll parameterize it this way: 2 m1 plus m2, and you will have a master. And this epsilon, well, I said it already, but let me remind you, epsilon is the mass of 3 minus the mass of 1 minus the mass of 2, okay? So if epsilon is positive, this state is above the mass of the corresponding threshold, and if it's negative, it's below, okay? And let me also stress that most of these states are above.
Why are you using non-relativistic effective theory as opposed to?
Because these systems are mostly, meaning the decay products, for example, or the typical momenta involved are relativistic because they're so close to threshold that they are necessarily much smaller than their mass. Okay. And in fact, now you have a separation of scales, meaning that the typical momenta over the Pion mass, and also the typical binding energy over the Pion mass. Systematic expansion. Okay, and then I allow for some cubic interaction of the 2 mesons in the exotic meson, and some quartic interaction for the meson self-coupled. Okay. So now we have a diagram of this sort, but this is the exotic meson who couples standard mesons, but we also have standard meson self-interaction. To be honest, since this is a non-relativistic effective theory, I need to be careful about arrows. These fields here will only contain either creation or annihilation operators, not both. Okay. Good. So I like this because, in my opinion, this is the clearer way. It's a clearer way of phrasing the problem. Meaning, the question is: this is an effective field theory that is valid for small velocity and at distances of the order of the Fermi or larger. Okay. So the question about exotic mesons, in my opinion, is the following: are exotic mesons states that are present in the spectrum of QCD already at distances of the order of the 1 Fermi? Meaning that in this effective field theory, should I put them by hand as another field, or are they dynamically generated by long distance interactions? I think that's the main question. Okay. Is this clear? Okay. Good. So now with this effective theory, I want to study the scattering of the 2 mesons together, okay, and see what information I can get about the. It's quite nice because I want to study what information I can get about the microscopic theory, the short distance theory, starting from long distance dynamics. Okay? And this is, let me say, this is just some rephrasing of an old argument by Weinberg is known as the Weinberg composite criterion. I'm just reformulating it in ERT language, okay? So I want to study these. Scattering of 1, 2, and 1, 2. Okay. And the nice thing about this theory is that it's simple enough that I can actually resum everything exactly. Okay. So there is a 3 level, and then I'm going to have all sorts of diagrams like these. One loop. And if you resum it, which is what Riccardo Ratazzi student Alfredo Ogliotti has done, you get this nice expression for the amplitude. Okay, so maybe this is worth putting up. You see it? Yeah. Okay, now what do I do with it? Well, first it's interesting, I think, to study bound states, meaning see what that amplitude does below pressure, okay? Whether if it has poles or not. Okay. And let me study the 2 extreme cases. The first case is the case where it does not exist a compact tetraquark, meaning these objects are not there in the spectrum at 1 Fermi, which G is equal to 0. Well, if G is equal to 0 and you ask yourself, do we have bound states, meaning I look for negative energies? Okay. In this case, you find that yes, of course, there is a bound state. B, which is 2 pi squared over mu cubed squared. Okay. And this is what the deuteron is. Okay, so you start from a theory that doesn't have any discrete level. You just have a continuum of self-interacting particles. And once you resum the bubbles, essentially, this generates a bound state. Okay. And in particular, you see that for this object to be a loosely bound state, you need a fine-tuning of lambda. Meaning that for microscopic reasons of whatever theory has generated lambda at short scales, this lambda is much larger than its typical size. And let me stress that the typical size of lambda is mass of the pion. No, sorry, it's 1 over mass of the pion. Okay. This you can guess it from dimensional analysis because this is a non-relativistic theory. So if you study the dimensions of lambda in terms of velocity, it turns out that lambda scales as 1 over velocity, which tells you how lambda scales with the cutoff. And then to fix the energy dimensions, you need to use the reduced mass. Okay. So if lambda is much larger than this B is much smaller. So let me say if lambda is much larger than 1 over m pi mu, then B is much smaller than m pi squared over mu, which is the standard binding energy you would expect. Okay. For deuteron, this is what happens. Okay.
So this is a factor of 5, like the
for the deuteron.
Instead of like m pi squared over.
That's right. For the
squared
deuteron
over 2m, right? Compared to b squared over 2m would have been 10 MeV or something. So, so the factor of 5 that you're talking about.
For the deuteron, yes. This guy is like, if this guy is a molecule, it's a deuteron on steroids. Because you see, the deuteron has a 2.2 MeV of binding energy. This has 100 keV.
Right.
It's like crazy, yeah. Okay.
So it's just tuned. It's just
crazy. I mean, this is tuned no matter what. Even if it's a tetraquark, I'll show you now that it's tuned no matter what.
oh,
This is, I think that the only difference, well, it's not even that much of a difference, because if you assume it's a molecule, then its tuning is at the level of the strength of the quartic coupling, which is anomalously large. If instead you think at it in terms of a tetraquark, the tuning is at the level of epsilon, where epsilon is whatever bare mass is generated by short distance QCD. You can do the calculation, I'll show you in a second with LHCb data, and it turns out that epsilon is like 100, no, let's say epsilon is like 0.1, so, you know, it's like 1 MeV or something like that, okay? Which is not as drastic as 100 keV, but it's still pretty fine-tuned. And then what happens is that it starts from a value that is, say, 1 MeV, so it's maybe tuned by a factor of 100.
isn't this just some? Isn't this another avatar of the problem? That this doesn't look like a. It doesn't look like a bounce state, like a big bounce state, right?
It does or it,
Huh?
it does or it doesn't.
It doesn't.
It doesn't.
Yeah.
Yeah, I mean, it depends, meaning that if I assume that tetraquarks are not part of the QCD spectrum, and this is a very big bound state according to them. I mean, it's extremely loosely bound, and so which makes it very large. See, now a priori, I'm not. Let me put it this way, maybe to be more honest. I'm not claiming that if I were able to build an experiment where I can take a D meson and a D star meson and put it sitting there at enough distance, they will not form a molecule. I think the claim, the question is more, do these tetraquarks exist at short distances? And is this what we are observing at colliders? It's a different story, right? Okay, good. The other thing instead is the other extreme is if I assume that for some reason, which is not going to be the case, but let me take the extreme experiment where there is no interaction between the mesons. Okay. And if you do that, it turns out that the bound state is dictated by an equation of this sort. But there is only the contribution from those diagrams that exchange the tetraquark. Which you see right away that since the right-hand side is positive, so it has to be the left-hand side, because if the tetraquark is above threshold to begin with, again, for reasons that we don't have control over, it will not generate the bound state below threshold. It will just dress himself with interaction, renormalize its mass, and that's it. And the second thing is that if instead the tetraquark starts below threshold, so that epsilon is negative, you will have a pole below threshold, but first of all, you'll have only one. It's what is the tetraquark itself, is just dressing. And B is always smaller than the magnitude of epsilon. So it's the interactions with the continuum that pushes the physical mass very close to threshold. Is this clear? And okay, so this is the bound state part. And now the question is, can we extract any information about what of these scenarios we are looking at from low energy scattering? Okay. And the answer is yes, as was super brilliantly realized by Weinberg. And the idea is that now you look at scattering for positive energies at low energy, okay? And we know that if we look at the scattering at low energy, let me now write it in terms of the momentum. So K is square root of 2 mu e. The amplitude is supposed to look like this. One. A. Fourth. This is a general thing, okay, for low energy scattering. I'm sure you know it, but just let me repeat it. The minus IK is forced by unitarity; it cannot be otherwise. Okay? And while instead the real part of the denominator depends on the macroscopic theory that you're looking at, and we only know that it's going to be an expansion in K of even powers. Okay, And this guy here is called the scattering length. And this guy here is called the effective range. But again, it's probably a repetition. And now you can ask yourself, okay, imagine that I'm scattering a dead star. What do I expect these guys to be? There is no that. Okay, and you can compute it, you just do a matching, no problem. And it turns out that the expression for the scattering length is like this. Pi lambda minus q squared over epsilon, and R0 is minus q squared over 2 pi x squared epsilon squared. Oh, and of course, I should be fair. I mean, this is an effective field theory, so every state I'm writing down, it comes with corrections. It comes with corrections that are inverse cutoff. Okay, and you see now this is crucial because. On the one hand, if I look at the scattering length can easily be anomalously large for two reasons. Either because I have a very large quartic coupling, meaning that these mesons interact strongly with each other, or because I have maybe a naturally large G, but a particularly fine-tuned mass for the third state. Okay? In both instances, you'll find a large scattering cross-section, scattering length. Okay, so this is not able to discriminate the two instances. What is able to discriminate the two instances is the effective range. Because if you observe an effective range that is negative and substantially larger than the cutoff, then it can only be due to a cubic coupling, okay? Which is the hallmark of the presence of this state already at short distances. Is this clear? Okay. And in fact, if you ask yourself what happens for the deuteron, well, the low energy data on deuteron tell you that the scattering length, experimental scattering length for deuteron is roughly 5.4 Fermi, and its effective range is roughly plus 1.7 Fermi. To be compared with the inverse pion mass, which is 1.4 Fermi, okay? So the deuteron has a large scattering length, but in these terms, a small effective range, small and positive, okay? So it's order 1 over m pi, and it's positive. Good. And now the thing that we realized recently is that LCB recently measured some parameters of that amplitude. They did not formulate it in terms of scattering length and effective range, but in principle, they have fitted the amplitude up to precisely order k squared, from which we can extract the scattering parameters. And what we found is that the measured scattering length for the X3872 is, well, I mean, it's ridiculously large. Fermi, which in principle doesn't tell you much about the state because, again, it could be a very loosely bound molecule or an tetraquark very near threshold. But the radius, the effective range, the experimental value of the effective range for the X is roughly minus 5.3. So it's negative, and it's consistently different from the cutoff. Cutoff again is 1.7, 1.4 Fermi. Okay. So this seems to me at least like an indication that there is a tetraquark in the Lagrangian. Okay. Again, another caveat of this, though, which is yet not settled, is that we have talked to LHCb. This created a whole mess. And the collaboration claims that their error analysis is not complete. So they are apparently publishing a V2 of the paper or a RATA or whatever where they do a more proper error analysis, and the error bands could become bigger, in which case this might not be. I'm not reporting error bars here, because if I report their error bars, this is like 20 sigma away from zero. Okay, so it's undoubtedly like this. But the claim is that there were some correlations between parameters in the fit that they don't control yet, and so the error analysis could be different. So it's not, this is not the final world. It could be that maybe they do the error analysis properly, and the error bar blows up, and then we cannot say anything anymore about RC. And this is yet to be seen. How am I doing time?
Yeah, maybe like 5 to 10 more minutes.
5 to 10 more minutes. Okay. Okay. Any question about this? Okay. Then let me go to the last topic, which is prompt production. I might not be able to talk about strangeness, but it doesn't matter much. Now it's going to be funny because I'm going to have to try to reproduce some experimental plots on the blackboard. Let's see how it goes. But the story about prompt production is actually started like a long time ago. I don't know, 2010 or something. By the simple fact that for the first time it was CDF back in the days, who observed the X1372 instead of, well, I think I erased it by now, but instead as produced from the decay of the B meson, as produced from the vertex of PP bar collisions. And they measured a prompt, this is what it's called prompt. Prompt is produced at the vertex, PP bar. X. They measured the cross section that ranges from 30 to 70 nanobars, which probably doesn't mean nothing yet, but to compare it, consider the cross section for the same process going in psi to S. The psi to S is the first excited state of the harmonium, so it's definitely a compact object. Okay, and this guy is produced with a cross section is 67 nanobars. So this seems to tell you that this guy here is produced with a similar mechanism as this guy is produced. Okay? And this is definitely CC bar, definitely compact, all that. Okay. And in fact, one can ask, how can I produce? So, sorry, I should say that this is for measurements of transverse momentum larger than 5 GeV. Okay. If you ask yourself, if this guy is a molecule, what is the typical relative momentum inside the molecule? It turns out that the RMS for that binding, because we know that we don't know exactly what the binding energy is. It could still be 0 within the error bars, but it's definitely smaller than 120 keV. If you use that as an upper bound, it turns out that this guy is smaller than 25 MeV. Okay. And so the question is, how can I manage to bind two mesons that in principle should have relative momentum of the order of this in order to bind from collisions of objects that have typical momentum skill set by that, so that's like 5 GeV or more. Okay. And this is a long, complicated story. First, maybe I'll just tell you the story without having to reproduce the plots. The story is that the first thing that people did, they were like, okay, I can estimate this from Monte Carlo simulations, because I can tell myself, okay, let me take Monte Carlo simulations and let me count how many times in a PP collision with the right energy I have DD bar mesons that have momentum smaller than that. Okay. And let me assume, by being extremely optimistic, that all the times that happens, that forms a molecule. Okay. You do that, and you find a cross section that is a factor of 100 smaller than the experimental one. Okay. But then there was question, because this, of course, depends on what you choose as the maximum momentum for the molecule to bind. So it's a bit questionable. So then, what we did later, we compared it directly to data, because we have data from CMS for the X produced at high PT, but we also have data from both CMS and Atlas for deuteron produced at, well, relatively high PT. Then they're not exactly the same value of the PT, which is a problem. But you can fit the curve with stuff that is well known and is well established. And it turns out that it does not seem like these guys produce like the deuterons. Like these guys seems to be produced not for 4 orders of magnitude more than the deuteron. And the last piece of information is very recently, is again by LHCb, that have observed this object compared to the set west, so precisely this, in high multiplicity collisions. High multiplicity collisions are proton-proton collisions, but that end up in a lot of final state particles, okay? And the idea is that these final state particles re-interact with your particles, the particles that you have produced. And again, it turns out that both the X3872 and the site west are suppressed by the presence of these additional particles, meaning you see less of them than in standard low multiplicity collisions, while the deuteron instead is enhanced. And the reason why it's enhanced is somewhat clear, is because the presence of the other particles can help you rescatter, decrease your relative momentum, and help the binding mechanism. And so again, this is another indication that at least qualitatively, this does not seem to behave like a molecule, but rather like a compound object like this. And I think I can finish here. Thanks.
Do you have any questions for Angelo?
People wonder whether this state could be like a CC bar and gluon, for example.
Yes, some people have thought about it. They're called hybrids. It's okay, some of them could, but some of them are charged. So they cannot be of that way. And of course, it's a priori, I don't think anyone is telling you that you can't have a situation where you have many of these states and they're all different things. Okay. I think for now, for economy of thoughts, people have focused on trying to find a single description for all of them. But the neutral ones, well, in particular, I don't think I have them here. There are other states who are neutral and are observed to decay most prominently in one of the Charmonia. Okay. And that's what triggered people to say, oh, well, maybe these are hybrids. It's that Charmonia plus a gluon, and what's just happening is that the gluon at a certain point hydronizes in a light vector and you're left with the original Charmonia. Okay. But again, this only applies to some of them. So it's a bit less stable.
This Tetraquark picture, is there an explanation why it's so close to the threshold?
Honestly, no, but the way I see it is it's landscape, if you want, meaning that there are, you see, as I showed you before, the interaction with the threshold pushes closer to the threshold, right? If you look at these states, most of these states are close to threshold, but not as close as the X3872. So it's not hard for me to imagine, but I might be wrong, that most of these have masses that are just natural, like 100 MeV away from threshold, and then the interaction pushes you down to 10 MeV. Okay. And the X3872 and this guy as well are the two particular cases where there is some accidental fine-tuning. Even the bare mass, it's already close to threshold by itself, and then the interaction pushes it even closer. But in the Tetraquark model, no, the idea is that bare masses are generated by short distance QCD. They are what they are. There are a lot of bare masses, there are a lot of thresholds. Sometimes some of them will fall close enough to the threshold.
Well, if there are no more questions.
Could you say a few words about the strangeness? Just to...
Yes, yes. It is still yet to be confirmed. Well, it's not the discovery is confirmed, but it's for now. I think it's more of an evocative fact. But the point is that I think less than 6 months ago they discovered 2 new states. You see, I think it's a very cool field because it's extremely data-driven. Experiments are very active. They discover a bunch of this stuff like yearly, and they discovered 2 new states, which are called the Z sub CS. Fantasy namings is not, which I think is 4 GeV mass, and then another guy which I don't remember what its mass is. Check it. Another guy whose mass is 3985. Okay, and they're called like this because these decays in d sub s minus and d 0 star, and these decays in g star a plus. So this is negatively charged, it's positively charged. So there is a strange quark in them, okay? And it turns out that if you look at their masses, you know, when you have strange quarks, there is this rule, it's called the halfway rule, the equal spacing rule, which is, I mean, it's somewhat trivial. It tells you that if you have a meson with no strange quarks and a meson with all strange quarks, a meson with only one strange quark is halfway between the two, okay? And if you look, for example, at the SU3 triplet of the X3872, this is the X, this is isospin and strangeness, okay? This is the X, these should be the neutral partners which have not been observed, okay? There is another state which I haven't told you about, but that has been observed. It's called the X4140, who's for sure SS bar. And you calculate the mean between these two masses. That's exactly 403. So it seems like this guy is filling this side of the multiplet. Which would be, so this multiplet would be completed if you weren't for the charge partners of the X. And then there is another multiplet which instead belongs to the Z sub C. So this is filled. So let me erase this because these are not there. This is filled. And the idea is that the other guy would be part of this. So that's Z sub CS, and allows you to predict what this guy would be. And there should be around 476 MeV. And this is, I think it's a nice feature because were it to be, if this were to be confirmed, if the multiplet were to be completed, I think this is unequivocally a tetraquark because meson molecules are not expected to fall into multiplets. Because when you start introducing strange quarks, the mediator that allows the binding of the molecule goes from the pion to the phi meson, for example. And the coupling between mesons and the pion and mesons and the phi are completely different. So no one tells you that they are the exact same thing, that they produce multiplets and stuff like that. But yeah, so this is still empty. It's more like an indication, like, oh, look, this guy falls precisely where it should fall, where it to be in the same SU3 multiplet. So it's quite nice. I mean, this is somewhat like we were when people were doing the eightfold way, filling the dots.
All right. Thank you again for the